Our goal this week is to evaluate limits not just graphically, but algebraically. So in order to do that, okay, we need some laws of how to do it. So these are our limit laws. Now in section 2.4, which we are not going to have any problems on, so it's basically something that you can watch the videos for if you were interested in learning about it. There we will give you the precise definition for a limit, not the sort of hand-wavy definition that we had last week, but an actual rigorous mathematical definition, and we can show how to prove with that definition all these kinds of laws that we're going to be using today. However, I'm not going to require that you watch those videos or those proofs. It's only if you're interested. So if you're not interested, you can just believe me when I say these are limit laws. What are they? So first of all, I want to point out the very top sentence here. If the limit as x goes to a of f of x and limit as x goes to a of g of x exists, and c is a constant, right? Because there's c here. But this is the important point. These laws are true when the limit exists. When one of those limits doesn't exist, then the laws aren't true. Okay? So if one of these guys is going off to infinity, or it's got some weird, oscillation going on or something, then all bets are off. We can't use these, but we would just say, all right, well, we can't use these, the limit doesn't exist, right? But once the limit does exist, we can use these. And they're very helpful because, as you see what this is telling me, if I look at this, it's telling me that the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. Okay, so it's nice. And it's even better now than here. If I've got a constant times a function, I can pull the constant out of the limit. So, for example, it's going to be 2 or 7 or whatever. So and then here, we've got the product. So the same thing is true of the product. I can pull the limit into each one of those f of x, g of x. And also the quotient. So the limit of the quotient is the quotient of the limits. Of course, for this one, you have to be careful. You have to make sure that you're not dividing by 0. You can see that's written down here because, of course, we can't divide by 0. That's the only case where it's a problem, right, because of the quotient. For all these, if one of these is 0, then it's 0. That's fine, right? So these are 5 limit laws. I'm going to write down some more. I ran out of space on the blackboard and only have 5. But what we're going to use these for is you can see immediately from the form of this, when we do stuff like this with the plus minus multiplication division, is when we're making more complicated functions, right? So we're taking some functions and we're making them more complicated. So we're looking at a rational function instead of a polynomial or something like that. So we are going to be able to use these laws with those kinds of functions. So let's keep going with the limit laws. I'm actually listing them the same way they have them in the book, just so that, it's consistent. It really doesn't matter which law is which. Nobody remembers what order their book listed them in. So it doesn't matter whether it's law 6 or 7, just in order to be kind of consistent. So the law 6 here is this. If I take f of x and multiply it by itself n times and then take the limit, I can basically pull the limit underneath here. And this is easy to prove with the law that I just erased down here, right? Because if I'm multiplying 2 functions, then it's the limit of the 2. So let's say you're just multiplying f by itself, right? You just get f squared, right? And if you're multiplying f by itself n times, you're going to get this. And then if you recursively use that same rule, you're going to get that. So basically, I can pull this limit underneath this power. Okay? And then turns out you can do that also with square root but it works. So this then is the nth root of this limit of f of x. Okay. And of course, it's going to, obviously, we're just going to take something in the proper domain, right? So this is not going to work if I'm taking the square root of a negative number, but we were just going to assume that we are going to be using this rule when this thing is defined, right? Now 8 and 9 are kind of nice, but very easy to see. The limit as x goes to a of some constant c, it's just a constant c because there's no x's, there's nothing to do. Graphically, what am I saying? It's very simple, right? So I've got some constant function y equals c, regardless of where a is. So a is here or there or whatever. That value of y is always c. So there's nothing exciting going on in that limit. It's just always c, right? So that's pretty easy to visualize. Another one that's pretty easy to visualize is the limit as x goes to a of x is just a. In this case, I want to think of not the line y equals c, but the line y equals x, right? So if I've got y equals x, that's just this line through the origin, and there's nothing fancy going on, right? There's no holes, there's no jumps, there's nothing exciting. Anytime I'm at some point A, if I go up there, my corresponding y value is also A, and as I go along that line, I'm clearly going to the point A. So that gives us this. Now what's very nice about this though, is that I can take this and shove it into here, and I immediately can see that now I can work with a few more interesting functions, right? So if I take here the function f of x equals x, that will just look like x to the n, and I know I can pull this limit in, and I know that that x just goes to a, so I immediately can just put in my a. And the same thing with the nth root. Oops, nth root of a, right? Nth root of x becomes nth root of a. So those are my limit laws. Now, I will one time, and only one time, because I hate to spend a lot of time writing things, go through an example where we very explicitly write which limit law we're using and everything, okay? So I will do this for you once, but I don't think I ever asked you to do it, and I don't know that I ever will. And so let me tell you what I mean. What did I have? So I had a problem written down here. That I want to do with all the steps. 4x squared minus 5x plus 6. You see, I was really thinking about that one. What numbers am I going to use? 4, 5, and 6. Okay, so because these are sums and differences, and also I'm not really worried about, I'm not getting a 0 in the denominator. I'll mention that later a little bit. So what I can do is I'll write it in 2 steps, right? First, I'm going to get rid of that. I'm going to take the limit of the top divided by the limit of the bottom, because this is a quotient, right? I think I need like 12 blackboards to do this if I'm writing out every step, okay? So you'll have to excuse me. And then I'm going to pull this guy into everything. So it's going to be limit as x goes to 3 of 4x squared minus the limit as x goes to 3 of 5x plus the limit as x goes to 3 of 6. And then the same thing in the bottom, I'm going to put the limit in front of everything individually. Okay? And now I'm going to pull out the constants because I said that was the thing I could do, right? So I can pull out the 4, the 5, and the 2. So 4, oh, I hope I don't run out of space. I have to start writing smaller than all this writing. And then the same thing down here, I'm going to pull out that 2. And now if I think about what I just had written up here, I can, that's a square, I can put in the 3. So when I evaluate this using that limit law, this is just going to be 3 squared. So let me just, I can put this in here. It's a little bit smaller, sorry about that. But it's going to be 4 times 3 squared minus 5 times 3. And that is just the limit of a constant, so it's just going to be 6. Same thing, it's going to be 2 times 3 minus 9. Okay, so 4 times 9 is 36 minus 15 plus 6. On this bottom is going to be 6 minus 9. So I have minus 3 in the bottom. And that is, 27, right? Because it's 30, but this one is just, is that right? 9? Yeah, that's right. Okay, so the answer is negative 1. Okay? Look, the thing is though, you're like, why did you have to write all that stuff? Because if you just went up in here and shoved in 3 into every x, you didn't have to write this whole board, you would get the answer. And that is actually 100% true. And that's why I said, I'm not going to make you write out every step, right? Because it's a waste of time and space. But now you see what you're doing, all right? It turns out you can just substitute in the x, okay? Then why even talk about the limit? Because you can substitute in the x, but only in this case, right? Everything has to exist. So, in my next video, I'll show you why this is important, and we'll look at some interesting things that we have to do in order to maybe get to the point where I can just shove in the number.